So as you know that yesterday we have I just missed the lecture due to some technical issues from my side. There was an issue of microphone, so I'm thinking that just to record this lecture and just given to you. Okay, so in this particular Y-by bending and Searle's apparatus, these are the two topic which remains in the last mod. I mean to say last topic of this particular module. Okay, and this module will be finished as on today. Okay. So we already discussed about the Y-by, I mean to say the Young's modulus, then bending moment and the cantilever. So now we have know about the relations about those depression produced because of the when you apply uh, force, or you say that couple is acting on the two ends of the what this particular beam. So there is a bending moment, and we have derived the formulas for those bending moments. So here the particular case we need to study, that's the depression of the beam supported at the end. So so when the beam is loaded at the center, okay, so what kind of shape it has when the beam is loaded at the center? So you can see that, so it is like two cantilevers you have, and they are in the inverted position, and you apply the weight, okay, at the middle of this or you say center of the beam. So let a beam be supported with the two knife edges we called as A and B over here. You can see in this particular figure, and this particular weight W which we apply or loaded at the middle of it. Okay, so the reaction force, or you say the equal opposite forces, that to be distributed equally on the right hand side as well as on the left hand side of this particular inverted kind of shape of a cantilever. Okay, so this bending of beam has the upward force, you say, which is at the end is W by 2 in the upward direction, and also at the B it is W by 2 again here. Okay, so you have a total weight that is to be equally distributed in a two ends, you say. Okay, or you say the two portions of the what the this inverted cantilever. So the middle part of the beam is horizontal here, and the beam may be considered as equivalent to two inverted cantilevers. That is what we just say. This cantilever is divided into two parts, like AC and BC equally, and they produce this bending because of the loads W by 2 acting upwards. That is at the what positions we say A and B over here. Okay, so therefore if the L we consider as the length of the beam AB, so length of the each cantilever AC and BC is L by 2. So the elevation of A or B above C, that is what is same thing that the depression of C below A and B. So it is like what we have, you can see over here in the figure. So just like a C is you have applied a weight, okay, and you plug the end A over there, okay, with some rigid support, you just, so there is a bending, okay, because of the weight that you apply at the free end C. Okay, similarly that's a B is like a plug, and you apply the force at the C, you have a what the depression produced. Okay, so that depression produced we already calculated in earlier equations or discussion, and that expression you know about this depression produced in terms of the Young's modulus of the material of the this particular beam. So what is that formula? These are the formulas we already have derived in earlier discussion. That is what depression produced in terms of the weight and length, in terms of the Young's modulus and the geometrical moment of inertia. And we know that this weight is expressed in terms of the Young's modulus as well as the what depression produced and the geometrical moment of inertia. So you, in this particular case, you have two cantilevers, inverted cantilevers, and they are having the what the length instead of L by 2, and the equal distribution of weight instead of W by 2, your new expression becomes, okay, W by 2 into L by 2 whole cube divided by thrice y AK square. So the depression produced, you can calculate it over here. Y is equal to WL cube upon 48 times y AK square. That is what you can just solve this mathematics, and you can get the final relation. That's what you have express your depression produce when, since you are applying the weight at the center and just plug the two ends of it, you will get this particular depression produce that you calculated. So AK square that we already mentioned is a geometrical cross section area. And if we say that what kind of geometrical cross section area do you have, whether it is a circular cross section or the rectangular cross section, depending on the value of that IG, or you say AK square, going to be a change. A is the area we mentioned, streamline area, K is the radius of gyration. uh, and suppose you have a circular cross section like a cylinder, you have a circular cross section at its radius, that is what pi r square. And if you consider a circular cross section for this, okay, so its value is here in this particular case of the beam will be a pi r square by 4. Okay, remember that. So this value we need to put over here and solve further to get the depression produced of such a particular case in terms of Young's modulus, in terms of the length, or you say in terms of radius of the cross section, that is coming inversely proportional to the fourth power of that radius of cross section. And suppose you if you have a beam of a rectangular cross section of particular breadth B and a certain thickness, you say depth has a D, and then we have this particular geometrical cross section value will be a AK square is equal to BD cube divided by 12. This derivation we already done in the first I mean to say last two lectures, where we have these kinds of geometry and talk about this geometrical cross section about the rectangular cross section. We know that this value, so we just put this value over here and solve further to get the depression produced in terms of the thickness, or you say breadth of this particular beam having the what the rectangular cross section area. So you can see that over here this depression produced is inversely proportional to the cube, okay, third power of D over there, okay, and directly proportional to L cube over there. So you can just express this formula just by calculate. If you know the how much depression is produced, okay, if you know that value, how much relative change to the original, to the how much when you apply the weight, that depression, if you calculate it for the particular weight, if you know that, you can easily calculate the value of Young's modulus. So these are the methods called as or this is the technique you can do in the laboratory of the F5 BSc Physics laboratory. When the situation is normal, you can do these experiments. So when the beam is now the second case, the case 2 we called, okay, now the earlier case we say that the weight is you apply at the what, just at the center of the what, the particular cantilever. So you have this earlier diagram, you talk about this W is what you just apply at the what, the center of this particular beam. Okay, now you apply those weight load uniformly. Okay, this is the what, the word uniformly over here. So when you say the word uniformly over here, okay, that's the what, the weight is distributed equally over the total length of the beam. Okay, so we consider over here small w be the load, that is per unit length of the beam. So capital L is the length of the beam and w be the load that per unit length of the beam. Total length acting on will be how much, you just apply the weight uniformly over here. So that is what center of, say that all the mass distribution over there is positioned at the what the center of that particular body. Okay, so here that CG position where we say having the central position, okay, and this has total weight which is acting downward is a W, capital W. So as we mentioned, this is again the reaction forces or those the knife edges you kept at the two positions over here, the A and B, and they are what they are at equally distribution from the center of this particular bended beam. But this beam is uniformly loaded, so all the weights that you put it equally on the what the total length of the beam. Okay, so here so when you say that this is the this is the what we have said that the reaction at the each knife edge is obviously half of WL acting upwards, with the beam being having as a system of two cantilevers, that is what fixed at position C. So consider again similarly that we derived in earlier derivations about the bending moments, considering that particular specimen, a small uniform cross section PQ over there, and which is placed at a certain distance X from the what the center of this particular beam. So and that's the similar thing we need to consider over here. But remember that here the distribution of those weights, okay, is basically taking on the what the half length of the beam. Okay, and this half length of the beam is what is actually L by 2. But since the specimen is held at a distance X, so that distance becomes L minus X over there. Okay, the weighted portion of the beam becomes L minus X. So weighted portion, if you multiply by the W into L minus X, that's the weight which is acting downwards. But that downward weight is acting on the half of the length or the average length of this L minus X, that is L minus X divided by 2 from the specimen section PQ. Therefore we need to calculate the bending moment about this particular section PQ. Remember that how we calculate. So just what the value you have, get it over here, half of W capital L into L minus X is the what the first, that is the what the weight we have because of the what the this particular specimen. Okay, the this what we say that the weight which is the acting downwards, okay, on this particular specimen, that is L minus X. But there is a equal opposite force that I say half of W so this particular force half of WL, okay, into L minus X will be the actual force which is which is opposite to the applied weight, you say. Okay, and therefore the resultant force you need to get minus, so subtracted, which weight we need to subtract it, that weight which has acting downwards. So resultant weight will be a what W that weight which is acting downward on the what the average length is a W into L minus X. That's the weight which is downward into how much length it is actually getting acting on it. So that what we say force into a distance, you say. Okay, that's a couple we need to minus from the what the upward couple. So resultant couple, that we say bending moment will be half of WL into L minus X minus W times L minus X into half of L minus X. Hope you people have understood how this expression comes. This expression is the resultant bending moment which we write because of the total weight which is distributed equally. But suppose we need to calculate it for the half portion, or is a particular section of this cantilever. Okay, so there is a weight which is acting downward is a half of WL into a what the average into the length L minus X. Okay, that's the weight which is acting downward, acting upward. So the downward force, downward couple, we need to minus from that upward one. So you can calculate the value of this bending moment over here. Okay, so you got this derivation. Now the thing is the similar that we have already been discussed in the earlier expressions also. What is the for the equilibrium case? There must be the moment of resistance to the bending, and that moment will be equals to yig by r. R is the radius of the curvature of the neutral axis pq you have, and that expression, that the resultant bending moment expression which you calculated for this particular case, you can write to the what the actual what we say moment of resistance to the bending, and that will be expressed in terms of Young's modulus and the geometrical moment of inertia and the radius of curvature. This expression you just write it over here by the earlier knowledge, or you say earlier discussion on the bending moment. So that expression I don't want to again discuss over here. This particular discussion we did in a discussion of those bending moments. Okay, so those expressions we just write it over here, how much the that particular depression that is produced. Okay, and that we write, okay, dy by dx in terms of that depression produced, small depression produced because of this particular bending on the particular what we say perpendicular to the length of the beam. So that that value we calculated already, and that value here it is written. Okay, that d theta dy, and then y is used to do while integrating this particular expression, and integration should be what within the limits that we called as a 0 to L over there. So here I am talking this particular derivation is on the what the total length, and you can calculate it by knowing the knowledge of your mathematical integration. You can easily calculate the values of this particular value we say L, which is what there instead of small l. Okay, if you put substitute the L by 2, why L by 2 over there? Because this is the weight which is acting on the what the half portion of the that particular uh, uh, half portion of the what cantilever. Okay, so therefore these limits of integration where we have L equivalent is not capital L over there, because there are the two cantilevers. Okay, you have, okay, but because of the uniform loading you say, okay, this has been divided into a two inverted cantilevers. So therefore your expression of y by bending becomes this way. Okay, this is the L4 to the power 48 minus L4 to the power 128, I think, and this gets solved further to get the value of depression produced. So here again that W is written in terms of the total length, capital W, and therefore you can express this depression produced in terms of the total weight of the beam. Okay, so in that way this calculation is done, and hope you understand how this formula been derived. Okay, for this particular case of y by bending, when you have a uniform loading on throughout the throughout the what the throughout the beam you have. Okay, uniform loading. So this is a particular case, and you have a different expressions that you derived and can be asked for any particular case to derive. So you have derive for this particular case when you have a this particular beam which is uniformly loaded. So you have this particular experiment you can do in the laboratory. Better way you are basically understand these experiments while doing this particular experiment in the first year laboratory. That's why by bending. So you people can do these experiments, also learn these experiments. Possibly we can plan some demonstration. If the situation is normal, we can try to do these practicals in the laboratory. Okay, and that time you people can easily understand what exactly is this y by bending, but this is the same expression you are going to use, okay, here in this particular experiment. So what I'm talking, this y by bending, that's Young's modulus of this particular material of the beam, okay, which is directly proportional to the cube of its length, inversely proportional to its breadth, and proportional to the cube of its inversely proportional to the cube of its breadth, sorry, depth, that you can say thickness as well, inversely proportional to the Young's modulus, and that is what you have a depression produce. Okay, so y and y, they are inversely related over here. So more will be the depression, okay, less will be the your Young's modulus, okay, or you vice versa, you can say that the Young's modulus of the material of these lace, okay, your depression produce will be a more in that case. There is a one experiment also which we called it as a Searle's apparatus. Might be you people have learned these experiments in your earlier courses of junior college, where we have the Young's modulus, determination of the Young's modulus by the Searle's apparatus. But this method also you are going to do in the laboratory, where you are actually determining the two elastic constants. That is what the Young's modulus and the modulus of rigidity for the material that which are to be compared, okay, here. So here in this particular case we are going to use bars, okay, and those are basically having in experiment rectangular cross section. So or maybe in some experiment they have a circular cross sections also, okay, but the way that experiment you can do here in the laboratory and understand what exactly this Searle's method for determination of the Young's modulus of the material of that particular beam over here. So here this particular experiment, this rectangular bars been used, okay, having typical rectangular cross section, and they are hanged with the wire and they connected with the wire also at its center of, and they just hang those wire to the rigid support, okay. And what we did, where we just when we have just give the force like a torque, okay, by just giving, you know, if we have a straight wire, okay, and we just made those 2 points or the two ends of those bars, okay, near to each other, okay, there will be a bending happens in the what this particular wire, and the arc is produced, okay. And that arc, you say that you can measure the length of this particular arc by how much angle is subtended at the center of this particular arc, okay. So this is the particular geometry you can basically understand. So theta is the angle between the what is angle subtended, half of the angle subtended at the center of this particular arc, you say, okay, and that gives me the radius of this particular curvature. If you have this particular curvature that you extended, so that center may be somewhere over here. So this center of this particular curvature has a radius r, and half of the angle which is subtended by one bar, you say, at its center will be a theta. Similarly over here, the another bar which makes an angle theta, so that total angle will be a twice of theta over here in this case. So these two bars will give me angle subtended at the center of this particular arc of radius uh, are having what we say, this particular arc, if we have a radius of curvature that r, and the angle that is subtended by two bars at its center will be a twice of theta. So if you know the radius, if you know the angle, so you can write the what is how much will be the what the length, okay, that what we say the length of this supposed to be a particular wire is L over here. So if you know the L is a length, okay, that you can express in terms of radius of curvature and the angle of subtended. So this radius of the arc is the r over here, okay, and the L is the length, and you can express this r, okay, that as a L over 2 theta. Now the bending moment of the wire and the couple exerted on each bar, that is what you have yig by r, and suppose it has a circular cross section, then you can use this pi r 4 to the power 4, and you can write the particular value of this bending moment in terms of Young's modulus by knowing the circular cross section. But what is this bending? We always talk about how much force is acting on the length, that particular ring, that couple, and that produces the angular acceleration. That is the what? The rate of change of angular velocity is the angular acceleration in each bar. So they accelerate, okay, with the velocity or angular velocity omega, and the rate at which this angular velocity going to be a change, which gives me a angular acceleration. So you have a torque which is like a moment of inertia into the what? The angular acceleration, that is what the alpha you have. So you have this alpha value is a d omega by dt over here in this case, and you can calculate the value of this particular what we say moment of inertia multiplied by this acceleration in terms of the Young's modulus. So here I is we are talking about the moment of inertia of the each bar. They have the masses, they have the distribution of masses, and that moves about an axis passing through the midpoint and perpendicular to its length. Therefore, they have the resultant moment of inertia that has a value I over there, and that is about the what we say a thread from which it is suspended. Thread means generally if it is a steel wire, they are suspended with the steel threads over there. Okay, it is not like a simple thread you have. Okay, so this d omega by dt you calculated as in terms of the Young's modulus, and this rate at which this angular velocity change we called as angular acceleration is proportional to the what, how much is the what this particular theta you have, means how much angle is subtended at the center. So more will be the acceleration, more will be the angle that subtended by that particular arc at its center. Okay, so the acceleration is proportional to the angular displacement. So theta is nothing but your angular displacement. Okay, so this the things we derived over here, and suppose these motions that we have are the, suppose means that actually these motions of this particular bar are like a simple harmonic motions basically. Okay, they just come and go to the extreme position, they have come to the center position, and those oscillations are uniform simple harmonic. Okay, then we can write down the time period for this each bar in terms of its Young's modulus, or in terms of its moment of inertia. This particular derivation I'm not giving you right now, but this particular oscillations, time period oscillation in SHM, okay, can be expressed in terms of this particular Young's modulus and moment of inertia. So this is like 2 pi root of twice Li divided by y into pi r to the power 4. Okay, and that expression which gives me a Young's modulus in terms of the time period of oscillations. Okay, that is a T1 and T2 are the simple harmonic motions of each bar. Okay, and since we consider this particular T1 and T2 are to be there are equally, but we need to determine what is the time period of this bar, because this time period is totally depending upon the how much moment of inertia of that bar. Yes, also depends upon the which material it is made up of and the what cross section and other things. So this expression is particularly calculated by knowing the how the time period is related to the moment of inertia, but you will get this derivation in a discussion of the moment of inertia. Okay, So this particular suspension that's we have, okay, and we have connected with the rigid support, and those suspension we connected with the what we say certain threads. Now in another case, if we remove these threads and we keep the one of the bar is clamped horizontally, you just attach this bar with the what wire, okay, and give a torsional oscillations. Means what, you just give a twist to that particular bar, just applying the forces at its end, okay. So what will happens, that will produce the what, the twist, or you say the twisting torque will be generated uh, inside the what we say the wire, okay, and that's what twisting the wire, okay. Basically you applying those forces uh, exactly tangentially to the what, the two ends, so torsional oscillations are produced, okay, and therefore its time period, suppose you called it as over here is a T2, okay, and that is related to the this particular twisting couple 2 pi root of I by C. So this twisting couple set up the in the wire per unit deflection of the twist, and it is equal to the what, n eta pi r to the power 4 twice L. Why it is eta over here in this case? Because those forces you apply are the what, along the what we say, or the tangential to the what, the direction, so of the what, the twisting. So there is a shear forces are developing inside the wire, and corresponding shear strain is you have, so that ratio gives me the modulus of rigidity, so eta, and that's what over here this particular eta comes, okay. So instead of y over here, your expression contains eta, and this eta is the modulus of rigidity. So remember that here how you are suspending the this particular bars. If you suspended the bar and you apply the forces perpendicular, then you can have the what, the computation of the Young's modulus. When you have applied those forces tangentially along the what we say surface of the those uh, bar, those particular wire, you say that the twisting wire torque which is generating, those forces are responsible are the shear forces, and the corresponding strain developed is a shear strain. Then you have a formula is for eta, okay. Here the y is here the couple which introduce the terms of the what, this eta over there, okay. So that's the reason you have a T2 has containing the term of eta over here, okay. So if you want to take this relation first, that you have a y expression, and relation 2 you have a eta expression, and if you want to take the ratio of this y over eta, okay, that's Young's modulus to the modulus of rigidity, you can have the ratio in terms of the time period, square of the time periods they have, okay. So the ratio of the Young's modulus, that is the coefficient of rigidity of the material of the wire in terms of T1, T2, that you can calculate it. And Poisson's ratio is a material of this particular Poisson's ratio you can write by knowing the y and eta. You can easily write the sigma in terms of the time period they have. So T2 is a time period when the bar is suspended suspended with the wire only, one of bar, while the T1 is a time period of oscillations when the bar is held with the what, wire, okay, and these two bars are actually suspended to the rigid support with the help of the thread. So Poisson's ratio of the material can be easily determined over here. So hope you understand this particular derivation. By the way, you people can do this experiment in the laboratory, okay, and this is a very simple experiment, but the expression that we derived, okay, here you can directly use over there to determine the Young's modulus of the material of that particular beam over here. So I just take one problem over here, a problem. You can get it these problems in this particular derivation from the book of Mathur. I have taken from it only. You already have this reference book. This particular problem contains a brass bar. Brass bar means bar is made up of brass material, and which has 1 centimeter square in a cross section. So area in cross section is given in CGS units. Okay, 1 centimeter square is supported on two knife edges. Okay, that is what 100 centimeter support apart. Okay, they are these two knife edges that we discuss, A and B. Okay, they are 100 centimeter apart, and you apply a load of 1 kg gram at the center of the bar. Okay, and why this 1 kilogram? This is 1 kg gram means 1 kilogram of the bar, that what depresses by the how much amount, 2.51 millimeter. That's the depression value you have, depresses by the this particular 2.51 millimeter. What is the Young's modulus of the bar? So it is the what depression that you have solution if you want to do, that is at the midpoint of the bar, and we already derived the formula for the depression produced. So and you know this bar is in rectangular cross section, so you can write the geometrical cross section area in terms of breadth. So you can know those formulas of depression produce and the Young's modulus, what we say geometrical cross section. You can easily calculate the value of what Young's modulus of the material. So this is the similar, I mean to say, the things you need to put it in a particular unit. So millimeter to be converted into the centimeter. All the units should be converted into the centimeter. So look at when you say a load, okay, it's a weight and the gravity acts on it. So 1 kg gram weight over there. So we need to multiply with the 980 or 981 dynes, okay, with this 1 kg or 1000 gram you say, so that you will calculate the actual weight over here. So okay, so remember W is like a mass into gravity. Okay, here W is mg. So this the is these are the CGS units calculations you did it over here, and you can calculate the values by substituting those values, and you can find out the Young's modulus been calculated over here in the CGS unit, which comes out to be a 9.77 into 10 to the power 11 dynes per centimeter square. But this value, if you want to calculate in Newton per meter square, so 1 Newton per meter square, which is equivalent to 10 dynes per centimeter square. So you can just divide it with this 10 dynes per centimeter square. So if you divide it by 10, so you will get the value of what this 9.77 10 to the power 10 as a modulus of Young's modulus of this particular brass over there in the SI units. You can solve those problems by putting all those units in the SI and try to solve. Okay, you will get the answer. Okay, so I think I'll just stop here. So if you have some questions, you please write to me. I have recorded this lecture for you because yesterday I've just missed lecture, and I will send you this lecture. But if you have some questions, please write to me. Okay, thank you.